So before we start talking about nucleophilic substitution reactions and the types and the mechanism, it's very important to cover another type of isomers. So if you don't remember what is isomerism and what are the different types of isomers, please refer to the second lecture, which we covered the topic of isomers. But I will quickly recap some of the types of isomers in order to get you to the point which isomer I'm going to talk about. So we talked about isomers and we said there are two types of isomers. There are structural isomers and there are the stereoisomers. So isomers are different compounds that have the same molecular formula, but they are different. So isomers must have the same molecular formula. Structure isomer, there were three types. I don't want to talk about them now because we already covered that before, but they are all different in they are different compounds which have different structures. Stereoisomers are compounds which have the exact same structure, but the arrangement of the groups in space are different. So we talked in the stereoisomer about two types, the conformational isomer. This is like the anti and the staggered form we find in alkane. And then we talked about there is another type that is called configurational isomers. Where in the configuration isomer there are two types. One of them we talked about last lecture, which was the cis and trans configuration of alkenes. So we talked about that last lecture. And the other type of configurational isomers is the enantiomers. So enantiomers is the type of configurational isomers we will be talking about today. The importance of the configurational isomer, the type, the enantiomers, is that it's very important to understand that because the different types of nucleophilic substitution reaction will give you different enantiomers. So let's first talk about what are enantiomers. So when you have a carbon atom, an sp3 carbon atom, it must be sp3, not an sp2 or an sp, so it must be a carbon in alkyl group or a carbon that is sp3. When it has when it's attached to four different groups, then it's called to be chiral. So a carbon atom that has four different groups, let's say something like carboxylic acid group, a hydroxyl group, a chloride, um, or a methyl and hydrogen, for example. So this carbon has four different groups. It's attached to four different groups. So this is called chiral carbon. Normally, when you have a chiral carbon, the four different groups that are attached to the carbon cannot switch places. So they will always have the same relative place in space that will be fixed. They will not switch places. So you cannot replace the OH with the carboxylic acid in space. Whatever the way you will rotate this whole molecule, always the four different group will have the same arrangement in space, okay, or the same relative arrangement. So their arrangement relative to each other will be similar. This carbon, as I said, is called chiral carbon. And any compound that has a chiral carbon atom will have another compound that is called enantiomers, and it's enantiomer, and the other carbon will be a mirror image of the first one. So a compound that has a chiral carbon atom will have another enantiomer or another isomer that will be a mirror image to it. Usually, these two mirror image compounds are non-superimposable, which means that you cannot have, however you rotate them, they will not be overlapping exactly the same on each other. They will always be mirror image to each other. So you have this compound here, and this is its mirror image. Each compound has a carbon atom that is attached to four different groups. They are exactly the same, and they are mirror image to each other. These two compounds are stereoisomers. They are not the same compound. They are different compounds. Although the enantiomers, they are called enantiomers. Although these two enantiomers have the same chemical properties and the same physical properties, but they are different. The main difference they do is that they rotate the plane polarized light in different direction. So the different enantiomers rotate the plane polarized light in different direction. This is the main difference. And because the groups are arranged in space differently, then they can have their biological properties can be different. So although their chemical and physical properties are the same, but if we recap from biology in GCSE or from A level, if we had any biology, you know that how there will be an interaction between a molecule and some sort of a receptor or an active site. So the arrangement of these group, because it's different, then they will have different biological activity. So this is why it's important to know what enantiomer are we dealing with. So how can we differentiate these two from each other? And when we name these compounds, how can we differentiate between them? In order to name the two different enantiomer, we give them letters, which are called R and S. So R and S are usually a prefix we give to the whole compound or in order to know where if it's actually which enantiomer is it. So how can we give the name R and S to our enantiomer, and how can we differentiate between them? So as I said, we need to have a chiral carbon, a carbon that is attached to four different groups. And then we start to look at these different groups and we will give them priority. We will number them from 1 to 4, depending on the priority. And to give the priority of the group, we will still apply the same rule we applied when we were giving the cis and trans names for alkenes, or the Z and E initial of alkenes as well, the different configurational isomers of alkene. So if you remember the priority, we will give them priority. So the priority increase with increase of the atomic number. So something like bromide will be given priority over chloride, over phosphorus, over oxygen, over carbon, which is over hydrogen. So hydrogen will always given the least priority because the atomic number of hydrogen is simply 1. If you have a lone pair of electron, it will be given even the least priority, but we are not actually talking much about having the lone pair of electron because all the enantiomers we are talking about is the one with the carbon, so there is no lone pair here. If we have a different alkyl substituents, as we said, we always look at the first point of difference. So you start off with the first atom, then the second, if it's the same, so we look at the second point of attachment and so on. So please, if you don't remember this rule, refer to the second lecture when we talked extensively about the rules for the priority. So as we said, we first start to give these different groups numbers. We don't move the groups from their place. We leave them as they are in their place, and we start to give them number from 1 to 4. So for a compound like this here, so we have the OH will be given the highest priority because the first atom attached to the carbon here is oxygen. Here it's a carbon. here it's a carbon, and here it's a hydrogen. So the oxygen will have priority over the carbon and hydrogen. So this is the highest priority, so this is given 1. And then here we have 2 carbon atoms. So let's look at the second point of difference. This is a carbon attached to 3 hydrogens. This is a carbon attached to oxygen, and oxygen with OH. This is a carboxylic acid group. So will be given priority over the methyl. So the carboxylic acid group will be given priority over the methyl. So this is going to be number 2, and the methyl is given number 3. And we know that the hydrogen is given number 4. Now, after we have given all our groups numbers, there is an important rule that because this is a tetrahedral structure, so only 3 groups can be in one plane, and the fourth group has to be in a different plane. You cannot have all 4 groups in the same plane. This is a 3D structure, and this is not in one plane. There are 2 planes here. So um, before you start naming the compound as R or as S, you must have the lowest priority group at the back, in the different plane at the back. And the other, you imagine that you are looking at the 3 other groups in front of you. So we need to ignore the fourth group completely. It has to be at the back, not in the same level as the other 3, or not in the same plane as the other 3 groups. When we draw the structure, in order to say that this group is actually at the back or at the other side, not in front of us, we give the bond this dashed, we give it this dashed form. So it's not a solid line. When the bond is a solid line, that means it's in front of us. When it's dashed like that, it means it's at the back. So always keep in mind that the group with the lowest priority, in order to give your compound R or S configuration, you always have to remember that the group with the lowest priority has to be at the back. Okay, so now I have the 3 groups, 1, 2, 3 now in one plane. They are in front of me, and now I need to look where to go when I follow the order of 1, 2, and 3. So for this compound, if you look, we are going this way. So we are going clockwise from 1 to 2 to 3. It's going clockwise. So this compound is called R. So if the arrangement from 1 to 2 to 3 is anti-clockwise, it will be called an S. So this compound, let's draw the mirror image of this compound. So the mirror image of this compound will have a carbon, the chiral carbon here. We're going to have the OH in the same place. We're going to have the carboxylic acid group in this direction, so it will be a mirror image of this one. And then we have the methyl on the other side, and then the hydrogen is still at the back. So this one is the mirror image of the other compound. Now let's give them the priority again. So the OH will be given number 1. The OH is given number 1. Then the carboxylic acid group is given number 2. And then the methyl is given 3. Hydrogen is given 4. Let's look at the arrangement now. So it's 1, 2 to 3. Now it's anti-clockwise. So this is an S. So if it's clockwise, it's going to be an R. If it's anti-clockwise, it's an S. Always remember that the 2 enantiomers, one of them will always be an R and the other one will always be an S. So if you draw the mirror image of your R isomer, stereoisomer, then the mirror image will be an S. And if you start off with an S and you draw the mirror image is going to be an R. This is very important to understand the difference between these 2 enantiomers, because when we talk in the next video about nucleophilic substitution reaction, you will find that actually the type of the reaction will affect the product which you get, whether it's an R or an S. Another important thing I would like to refer to as well, if you have the both enantiomers, the R and S, in the same mixture, we usually call this racemic mixture. So it's called racemic mixture. So a racemic mixture is simply a mixture of the S and R isomers of the same compound. You can have only one isomer in a solution or even as a solid or a liquid, or you can have a mixture of these both isomers. If you have a mixture of both isomers, then it's called racemic mixture.